This is a quick tutorial to review the dynamics of one-dimensional ODEs as we had in the last lecture. We begin with a function that describes the rate of change of something. So we began with some y prime that was equal to, as we began, was 0, so we know that there is no change. So a function over time would evolve like this, and so this is our f of y, which is the y prime when the y prime is 0. If our y prime is a constant, then we have the evolution of that variable summing a little bit at a time, but that amount that is being summed is constant, so we have a constant rise. And if we have that function being, that rate of change being a function of where we are, then we get some sort of exponential. In the case that it's positive, we get a rising exponential. In the case that is negative, rising to infinity. And in the case that is negative, we have an exponential fall. Right? Now, knowing this is very interesting, and it's very easy to compute qualitatively the end states of a certain trajectory. So I call a trajectory a solution to the differential equation. So if our differential equation, for example, is some cubic, you remember I spoke about the cubic before, say y cube, then the solution to that differential equation would look something like this. And if we have then an initial state here, Mr. y0, then because it's under the curve, like the rate of change here would be positive, and so this state would move away from this point here, the equilibrium. Similarly, if we're at the left of the curve, we're going to move ever accelerating to the left side of the curve. And so this is the negative domain. We call this a repeller. If we multiply that y cube, for example, by minus, let me actually put it in the same graph here, minus y cube, and then I'm going to plot it here. Now you'll see that the behavior of the equilibrium changes. It starts to attract these orbits or trajectories that are representing the initial states, many initial states of y0 here. Now we can also parameterize the differential equations in different ways. So for instance, we could have here a parabola parameterized by a certain constant. And this parameterization would then change the behavior of the dynamical system described by this equation as a function of this constant. So this constant we call a parameter. So as we had in class, if in this case this constant is larger than 0, then we have no equilibrium states whatsoever, and all of what the states do is move to the right. It moves slower, close to the bottom of the parabola, but then increasingly faster as we move to the side branches. If the constant is equal to 0, we have what we call the saddle node behavior. And if the constant is smaller than 0, we have the emergence of two equilibrium states, one of which is attracting, and so this attracting, and this is repelling. Now, for one-dimensional dynamical systems, which are represented by some function, some arbitrary function, the number of equilibria is going to be determined by how many times it crosses the zero line, and the type of equilibrium is going to be defined by whether the domains on the left and on the right. So in this case here we have a plus, it's here a minus, a plus, minus, plus, minus. Then it very clearly, so these trajectories are going to the left, these ones are going to the right, and hence this guy here is a repeller, for example. Practice this, and you will know almost everything that there is to know about one-dimensional dynamical systems, such as the ones that represent the activation variables in the Hodgkin and Huxley model.